Hey guys, hope everybody's doing okay. What we're going to do today is take a look at an extension of intermolecular forces and see how that applies to physical properties of materials. The strength of attraction between particles can greatly affect some of these properties of a substance or of a solution. So we're going to look at some of those. Some of these were talked about very briefly in Honors Chem, but we're going to go into a little bit more detail today and take a look at a couple more properties that were not previously mentioned. So the first one is viscosity. Viscosity is the resistance of a liquid to flow. So you want to think of it maybe as the thickness of a liquid. So a liquid that is very resistant to flow is typically thicker, right? A thicker liquid wouldn't want to flow. It's more resistant to it than a thin liquid. So how does viscosity relate to what the intermolecular forces are of a substance? It's really right here. It's related to the ease in which molecules can move past each other. So you want to think of it in this way. If molecules can move past each other pretty easily, you're going to have a thinner liquid, right? If particles are more attracted to each other and have a harder time moving past one another, then it's going to be thicker and it's going to be stronger intermolecular forces and be held together a little bit better. All right? So viscosity is going to increase with stronger intermolecular forces. It'll also decrease with higher temperature. So let's analyze those two things really quick. I have a bunch of hexanes or alkanes down here. Okay. Hexane is only with 6 carbons, okay? Heptanes with 7, octanes with 8, nonanes with 9, decanes with 10. So from our previous lesson, if you have a longer alkane chain, right, and therefore there's more mass here as well, if you have another decane near this, it's going to have a stronger attraction than if you had 2 hexane molecules next to each other, okay? There's 10 carbons and a lot of hydrogens, a lot of locations for that London dispersion attraction to occur. Okay, with hexane, there are less locations for that to occur, so it's a weaker intermolecular force. So you can see decane has a higher viscosity than hexane does. So stronger intermolecular force, thicker the substance, more resistant to flow. Viscosity decreases with temperature because as the temperature goes up, particles move faster, right? So as the particles move faster, they're able to move past each other a little bit easier, right? So higher temperature means faster particle movement, easier for them to move past one another, and then a lower viscosity, all right? So this has to do with engine oil a lot. So that's one of the main examples I use when I talk about viscosity. You want an engine oil in your car that is going to be like a little bit thinner in the winter time when it's cold, right? Because the particles are going to move slower. So you don't want the particles to move too slow, and you don't want it to be too thick of an oil in your car. And in the summertime, when it's hot, you want the oil to be thicker. So you want to make sure, like there's types of oils that have temperature ranges. Okay, so they are a little bit, they act a little bit thinner in the winter time when it's cold, and they're not too thick. And in the summertime, they act like a little bit thicker. They're not too thin and too light. Okay, so depends on where you live, what type of vehicle. You can find all sorts of different types of oils that have viscosity ratings and temperature ratings, and that's what you want to pick the right one. Okay. Boiling point and melting point was kind of talked about already. So the higher the attractive forces between particles, the higher the boiling point or higher the melting point is going to be. So the end of the intermolecular forces lecture went over an example, I think, with melting point, and I went over that one. So you can see a couple examples here. So fructose, obviously a type of sugar, has a boiling point of 440, and then you have all the way down here to acetone, which is a boiling point of 56. Fructose is a bigger molecule, okay, more attractive forces there, higher boiling point. Mercury is metallic bonding, which was one of our stronger forces of attraction. Because of that sieve electrons, that's a high melting point as well. And then, look at water. Even though it has hydrogen bonding, it's still pretty small, right? So the boiling point is 100 degrees there, which is much less than sugar, which is which is a solid at room temperature because of the stronger intermolecular forces. So that's your trend with melting point and boiling point. Okay, the next one's cohesion and adhesion. So cohesion is the attraction of a substance to itself, and adhesion is the attraction of a substance to some surrounding item. All right, so a little image there to help you understand that. Water has very good cohesion, and depending on what you are putting water next to, it has pretty good adhesion with that as well. So the stronger the attractive forces between particles, the stronger the cohesion is going to be. Obviously, the stronger the attractive force between some substance and another substance, the stronger the adhesive forces are going to be. All right, so I have two liquids here on wax paper. You should know that wax is very nonpolar, okay? So you can do a beading test, that's what this is, where you can take two substances, put them on wax paper, and see which one beads up better. Then you'll be able to determine which one has a greater polarity, okay? So you can see that the liquid on the left is water, okay? Water is very polar, we know that. Wax paper is very nonpolar. So the water is going to try to get away from that wax paper as much as it can. It can't get away from it completely. It can't hover over the paper, right? It's going to get away from it as much as it can and bead up very well. So it's trying to be very cohesive here and not very adhesive. This is rubbing alcohol, which is still polar, okay? It's just, depending on what alcohol it is, it's less polar than water. Alcohol usually has a carbon chain on it. It could vary in size. Okay, that carbon chain is going to give it the nonpolar property. And the OH group on the end of an alcohol is going to give it its polar property. It all depends on how big that chain is. But you can see it's a little bit more attracted to the wax paper because it's a little bit more nonpolar. So you can see it spreads out a little bit more. So you look at the angle and see which one is the better beading property here. So stronger intermolecular forces with water to itself, hydrogen bonding, very strong. So more cohesion there, less cohesion for the alcohol, and obviously there'd be more adhesion here and less adhesion here for the water. So here's your balancing act here. The strength of adhesion depends on the attractive forces between the liquid and the surface, and how strong are the cohesive forces as well. So water's cohesion doesn't change, but its beading depends on the adhesion to the surface. Depending on what surface you put it on, it'll bead either better or less. So when water is on a nonpolar surface like wax, it beads very well. The cohesive forces of water are consistent between this image on the left and this one on the right. So water, again, on the right has the same cohesive forces. It's attracted to itself with that hydrogen bonding. But if you put it on a polar surface, maybe something that's painted, which has a relatively decent polarity to it, you're going to see that the water is going to bead bead less, okay, and spread out a little bit more. You see that here. Sometimes you have these different treatments on maybe for your car, like if you have leather seats in your car, you might have a treatment that is put on it. You buy a solution or something at the store, and you apply it to the seats and to the leather parts of the car, and that's so if you spill something on it, it doesn't like soak in, right? So you can see like the left-hand side of this surface was treated with something like that, and the right-hand side of this was not treated with it. You can see that the water is beating up very well here, trying to get away from that surface that was treated, and over here on the untreated surface, it is spreading out and taking up more space pretty easily. So, which of these, water or alcohol, is attracted to the wax paper? You can see the rubbing alcohol is, and the water is less attracted to it. So we talked about that a little bit. Knowing that the wax paper is nonpolar. And you can see the difference on a paper towel, where the paper towel is polar, okay? Well, that's on the next slide, I'll show you that. And here's your wax paper. So the water beads better on the wax paper, and the rubbing alcohol is less attracted to the paper towel because it is polar and the alcohol is less polar. Okay, so beading has to do with obviously cohesive forces and whatever substance you have it on. And it also has to do with the attraction to the surface, like I said, and of course the force of gravity, which is consistent here, because we're doing all these on Earth. Okay, capillary action is the next one, and this is the ability of a liquid to flow through a narrow space without assistance, even in opposition of gravity. So you probably talked about this in biology a little bit, capillary action. You talked about plants, I'm assuming. We're not going to talk about plants very much here in AP Chem, but we could look at something like this, where you have some different glass tubing it's open on both ends, and you put it in this liquid. You can see the liquid moving up these tubes to various distance, like to various points, right? Let's take a look at how this works. Another example is maybe you have something like this in your basement. I mean, I hope you don't, but if you have some moisture in your basement or a little bit of water, and you have cinder block foundation, you see that some of the water travels up that wall. That's capillary action in a real life situation right there. So polar liquids like water will exhibit capillary action in narrow tubes of polar materials like glass, or charged materials due to adhesion. So the liquid will go up higher in a thinner tube, just a little bit easier to go up higher in the thinner tube than a thicker tube, but the amount of liquid going up the tube is actually the same. So if you have two glass tubes, one is narrower and one is thicker, if you took the amount of water here and the amount of water here, you'd see that they are the same. Okay? Water is not going to go up this plastic tube very much because water is very polar. Plastic is very nonpolar. So right here, due to adhesion, there's hardly any adhesion between glass and plastic. So you're not going to have good capillary action here. Okay? The more polar your surface is, higher the liquid, if it's water, is going to go up. So, little summary of capillary action depends on cohesive forces between molecules, adhesion forces between the molecules in the tube, how thick the tube is, what's the diameter, and of course the force of gravity. This is what I wanted to mention a few slides ago when I was talking about the paper and how the water spread out on the paper very easily and rubbing alcohol didn't. If you look at paper, you have cellulose, which is this. In paper products, look, you have a lot of OH, 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 hydroxide groups. A lot of good polarity there, right, with oxygen and hydrogen. A little bit of potentially hydrogen bonding, depending on what else is around it here. So that's what makes the paper polar, is because of all these OH groups here and those partial charges that are associated with that. And you can see glass is polar as well because you have a very electronegative element in oxygen present in a lot of it. Okay, so that's what gives glass and paper its polarity. Other examples of capillary action I think are really relevant and pretty neat. Wicking for a candle. So when a candle's burning, it's really the wax that's burning. So you have a wick, right? So wicking, we'll talk about more of that in just a second. But the wax melts, and the wax soaks into that wick, and then it burns. And of course, the wax is flammable. So you can see, that's the example here. Moisture wicking clothing, if you have clothing like this. We talked about earlier in the unit that evaporation is a cooling process. So clothing like this actually pulls the sweat away from your body. Okay, it wicks the sweat up, all right, through capillary action. It helps it evaporate, and when it evaporates, it cools. So evaporation is that cooling process. So clothing like this is meant to cool you down by speeding up that rate of evaporation by pulling that sweat away from your body. Paper towels are an example of capillary action. Paper towels soaking up water. You can say like the paper towels at school are, the capillary action is not very good. Am I right? You need a million paper towels to clean up like the smallest spill. And here we go with the biology example, vascular tissue in plants. Okay. Next one is chromatography. And we talked about this in Chem 1 a little bit. Method of separating mixtures that takes advantage of different levels of adhesion to a solvent. Main example is thin paper or thin layer chromatography, paper chromatography. So we did a little mini experiment like this in Chem 1, I'm pretty sure. So you have some paper, right? Chromatography paper. You put a line of, like, let's say a marker on a piece of paper. You dip it in a solvent, usually water, sometimes a version of like some type of rubbing alcohol. And you dip that paper in. The solvent starts to soak into the paper through capillary action, the last thing we talked about, and it moves up. And it's going to take some of those dyes, if it's a mixture, with it. Okay, let's check it out. Okay, solvent soaks up, and look at the dyes of your marker separate. Okay, those colors most attracted to the solvent rise up the farthest. So if the solvent is water, it's very polar, right? So that means the polar dye will travel and be attracted to the water more, so it travels up the paper more. In this case, red, it didn't go as far. So there's still some attraction to that water solvent, not as much, okay? So yellow, if the solvent's water, okay? Yellow would be the most polar, and red would be the least polar. All right, try to look at that one more time just so you can see it. Okay, solvent soaks up, less polar substance doesn't travel as far, more polar substances travel further because they're attracted, okay, to that solvent more through the intermolecular forces, right? Another example of this, I did a few labs that involved this in college. A lot of you guys will probably do the same thing. It's gas chromatography. So it works the same way. You have an inert gas like nitrogen that pushes a sample through a big column, like tubing, in an oven, okay? That heats it up. So in that column wall, you have all of these like molecules here, okay? Let's see if it says what they actually are. They're all different, like carbon chains. So this is right here, polymer chain. Polymer is just a big, huge molecule, okay? They're nonpolar. And your gas is going to push your sample through that column. And you can see the, kind of trying to add some humor to this here. You can see some of the components of your sample that you're analyzing. If they're polar, they're not going to be attracted to that column wall very much. So they're going to stay behind, okay? Non-polar, I'm sorry, very polar, okay, won't stick, all right? So they're actually going to go flying through. The non-polar components, they get stuck to the column wall, right? Because they're attracted to it. So they're going to go slower through that column. This is used to analyze a lot of different things. It's used in a real life scenario. Hopefully it doesn't apply to you, but sometimes if you get somebody gets pulled over and the police officer suspects not good things are occurring, you take a urine test or a blood test. They could run gas chromatography on that, and hopefully it comes out clean. But you can see different components will travel through more, and they could see what was in your system when you were pulled over. Again, hopefully it's nothing bad, right? So non-polar components are attracted to the wall. They stick to it, right? They don't travel as far. The non-polar component, or the polar components, will fly out. They'll come out first. And you'll see this readout at the end. And you can see what like the different peaks are. You can see what came out of the gas chromatography machine first, all the way through last. Really neat if you get a chance to do that in college. Okay, a couple more. Surface tension. You can see that water is what we're going to use for that. Water has hydrogen bonding, and you can see that with the hydrogen bonding, you have water molecules all around. So you have pulls going in all sorts of directions here. At the surface, though, you have on the slide right here. you don't have an upward, there's no water molecule like above the surface, right? You don't have an upward pull over here. You have pulls going left and right. You have downward pulls. Nothing up to cancel this out. So what does that create? It creates a little bit of like a tighter layer, okay, or a more attractive layer at the top here. And a net inward force, okay, going down on that surface actually creates a little bit of a harder surface to break through. Okay, so you can see the picture here of this water bug. You can actually see the water bending. Okay, that's that layer at the top. Okay, with that net inward force, creating a tougher layer to break through. So if it's really light, it's not breaking through that layer. You can see it's really neat. You see the water actually bending, and you picture these molecules actually bending in a little bit, and the legs of this little bug not breaking through. So I think that's pretty cool. Okay, last one here really is evaporation and vapor pressure. So we're going to do a lab with this, hopefully. What effect do intermolecular forces have on the rate of evaporation? Just think about it a little bit. If you have a substance with strong intermolecular forces, in order for the particles to evaporate, they need to move faster, right, and break that attraction. Liquids have a decent amount of attraction. Gases have hardly any, really none. So in order to go from a liquid to a gas, you need to break that force of attraction that the liquid molecules have. So the stronger that attraction, the harder it's going to be to break it. Therefore, the higher temperature you're going to need. Okay? When a substance evaporates, we already mentioned this, it's a cooling process. So you can see, like water, take the initial temperature of water, you have a thermometer in there, you remove the thermometer and hold it in the air, and the water will start to evaporate. You can see water has hydrogen bonding, so the temperature doesn't really drop, so not much evaporated. But if you look at methyl alcohol, it has a carbon group attached to the OH. So it's a little bit more nonpolar. So the attractive forces are a little bit weaker, okay? And you can see that the initial temperature is 25, and then it goes down to 20.2, which shows you that it evaporated, okay? So we'll do a lab with this, hopefully, like I said, and we're going to look at the intermolecular forces of attraction of a bunch of things, and we're going to see what does the temperature drop to. That'll show us which ones evaporate very easily and which ones are not evaporating well at all. This ties into vapor pressure because if you think of a flask with a stopper on it, you have a liquid in it, okay? Some of that liquid will evaporate and fill up the flask, okay? That's vapor pressure. So you have your liquid here, you have particles evaporating and really condensing at the same time. That's equilibrium. That's next unit. It's unit 3. But you can see that there are particles in here that are in the gas state. That creates a pressure. So that's what we call vapor pressure. So the resulting pressure from the gas particles is vapor pressure. And depending on your liquid, you're going to have a higher or a lower vapor pressure. So if you look at these two examples here, you have liquid A and liquid B. Both of the liquids below are at the same temperature. All right? Predict which liquid has the stronger intermolecular force. So students get confused by this sometimes because you have to think a little bit. The pressure here is a little bit above 0. Pressure here is about 2. Let's just say atmospheres. I don't know what it is. Both liquids are here, A and B. Liquid A clearly evaporated less. Liquid B evaporated more, has a higher vapor pressure. The temperature is the same, okay? So what's that mean? It means liquid B, which is the same temperature as A, evaporated much, much easier, right? It was easier for liquid B to break the attractive forces in that liquid. It was harder for letter A, for liquid A, to break its attractive forces, meaning the attractive forces on A are stronger. So liquid A has the stronger intermolecular force, harder to break that force of attraction, less particles in the gas state. For letter B, easier to break that force of attraction, more particles in the gas state, higher vapor pressure. Okay, so that's how you want to think of that. Final slide. The boiling point, we'll revisit this in Unit 3 as well. The boiling point of a liquid is the temperature at which its vapor pressure equals the atmospheric pressure. You'll analyze these later, but the vapor pressure is on the y-axis and the unit is in torr. 760 torr is the same as 760 millimeters of mercury. That is standard air pressure. So diethyl ether, which is relatively nonpolar, okay? Boiling point of 34.6 degrees Celsius, okay? If you did an experiment, the vapor pressure would be equal to the atmospheric pressure at 34.6 Celsius. Ethanol, which is 2 carbon groups and an OH, which has some polarity to it then, right? A little bit more polar, so higher boiling point. Water, extremely polar, hydrogen bonding, boiling point of 100 degrees Celsius. So you can see that diethyl ether has a weaker intermolecular force, okay? Because it only takes 34.6 degrees Celsius to boil it, right? That's what the boiling point is. It's right here at that 760 torr line. Water's boiling point is 100 Celsius. A lot more energy required to break the attractive forces in water, 100 degrees, versus the attractive forces in diethyl ether, which only took 34.6 degrees Celsius, of your temperature, your kinetic energy, to break the attractive forces there. Okay? I think that takes care of it. So a little bit more in depth compared to Chem 1. A little bit of it is a repeat, but that covers all of the physical properties and how they relate to intermolecular forces. We'll talk about it a little bit more in class. If you have any questions, let me know. That should be about it. Thanks, guys.